30 Advanced Test Automation Scenarios, the Architect's Playbook.
Anyone can write a Selenium script that opens a browser. But can you build a framework that runs 5,000 tests in parallel, integrates with Jenkins, handles flaky data, and self-heals when the UI changes? That is the difference between a junior tester and an automation architect.
From scripting to architecture.
Today, we are going through 30 real-world advanced automation scenarios. We aren't just looking at syntax. We are looking at design patterns, infrastructure, and resilience. I'm going to show you the mistakes that kill frameworks at scale and the architectural patterns that solve them.
What we will cover is:
We will break down 30 scenarios across 6 critical domains. 1. Framework architecture, thread safety, and design patterns. 2. Reliability and synchronization killing flakiness. 3. Test data management, state injection, and a PI setup. 4. CI/CD integration, Docker, pipelines, and reporting. 5. Microservices testing, contracts, and mocking. 6. Specialized testing, security, and accessibility. For each scenario, we will look at the before code, the anti-pattern, the after code, the architect's solution, and I will throw a curveball question to test your depth. Let's dive in.
Category 1. Framework architecture and design patterns.
We start here because the skeleton determines the lifespan of your automation. If you get the architecture wrong, specifically regarding how you manage browser sessions and state, your tests will become unstable the moment you try to scale. These scenarios focus on building a robust foundation.
Scenario 1. The thread safety trap in parallel execution.
You have a suite of 500 automated tests. They run perfectly when executed one by one. But the moment you configure your test ng or JUnit to run in parallel to save time, the suite explodes. Browsers close randomly, tests fail with session not found, and data from test appears in test B. How do you architect a framework to handle thread safety? Before code problem, the static WebDriver anti-pattern. Disclaimer: always test code in a non-production environment. This is the root cause. By declaring the driver as static, you create a single class-level variable. If you run 5 threads in parallel, all 5 threads fight over this one driver instance. Thread A opens a URL, and thread B immediately overwrites it. It gets worse here. When thread A finishes, it calls driver.quit parentheses. Since the variable is shared, this kills the browser session for thread B, C, and D instantly, causing them all to crash.
The solution: thread local isolation.
To solve this, we do not just remove static. We implement the thread local design pattern. This tells the Java Virtual Machine, JVM, to create a separate isolated container for the WebDriver for each running thread. Thread A gets its own driver, thread B gets its own, and they never touch each other. After code solution: implementing thread local. Disclaimer: always test code in a non-production environment. We define driver ref as a thread local. This creates a unique box for every single thread. Even though it is static, the content inside it is unique to the current thread context. When a test step needs the browser, it calls getDriver parentheses. The JVM looks up the specific thread calling the method and returns only the driver assigned to that thread.
Follow-up 1. Why not just remove the static keyword and make it a normal instance variable?
Answer: it solves the threading issue, but it breaks the shared state capability. We often need to access the driver in listeners for taking screenshots on failure or utility classes. If the driver is not globally accessible via a thread-safe static method, you have to pass the driver instance to every single utility method, creating messy code.
Follow-up 2. How does this pattern impact parallel reporting logs? For example, extent reports.
Answer: reporting has the exact same problem. Just like the driver, the test object in your reporting tool must also be wrapped in a thread local. Otherwise, logs from test A will randomly appear in the report for test B, making debugging impossible.
Follow-up curveball. What happens if you forget to call driverref.remove parentheses at the end of the test?
Answer: you cause a memory leak. Thread local variables are not automatically garbage collected when the thread returns to the thread pool, common in test ng runners. The driver reference stays in memory, attached to the thread. Over thousands of tests, this will consume all heap memory and crash the execution grid.
Pro tip: the factory extension.
Do not just put new Chrome driver parentheses in your setup. Combine thread local with the factory pattern. Create a driver factory class that accepts a browser name from your CICD parameter and returns the correct driver. This makes your framework browser agnostic and ready for grid execution immediately.
Scenario 2, POM versus screenplay pattern.
The page object model, POM, is the industry standard, but it has a fatal flaw at scale. It violates the open or closed principle. As your application grows, your page classes become God classes with thousands of lines of code. If a login flow changes, you modify the same massive file that handles registration, breaking the single responsibility principle. Modern enterprises are moving to the screenplay pattern to fix this. Before code problem, the bloated page object. Disclaimer, always test code in a non-production environment. In POM, we couple the data locators with the behavior methods. This structure encourages vertical growth. Every new feature on the login page requires adding more lines to this specific file. This is where it breaks. A single class ends up handling happy paths, negative scenarios, and edge cases. This becomes a maintenance nightmare where one syntax error breaks every test relying on the login page.
The solution, the screenplay pattern.
The screenplay pattern refactors automation into actors, tasks, and interactions. Instead of a page having methods, we create small, reusable classes for every action like a login task. This adheres to solid principles. Classes are small, single-purpose, and composed together rather than inherited. After code solution, composable tasks. Disclaimer, always test code in a non-production environment. Instead of a page, we have a task. This class does exactly one thing, log the user in. If the login logic changes, we only touch this file. Other interactions on the login page, like reset password, would be their own separate classes. The logic reads like English, actor attempts to enter value. This high-level readability separates the intent of the test from the low-level Selenium implementation details.
Follow-up 1 is not creating a class for every single action overkill. Does not it create file bloat?
Answer, it creates more files, yes, but it reduces complexity. In POM, you have fewer files, but they are massive and tightly coupled. In Screenplay, you have many small, decoupled files. It is much easier to maintain 100 small, simple classes than 10 massive, complex ones.
Follow-up 2, how does this help with reporting?
Answer, Screenplay provides living documentation out of the box. Because the code is structured as actor attempts to task, the reporting engine, like Serenity, can log every step in plain English automatically. In POM, you have to manually add log.info parentheses steps everywhere to get the same readability.
Follow-up, curveball. Can you implement Screenplay without a heavy framework like Serenity BDD?
Answer, yes. Screenplay is just a design pattern, not a tool. You can implement a lightweight version in raw Java or TypeScript by creating a simple actor class and a task interface. However, frameworks like Serenity handle the heavy lifting, reporting, driver management for you.
Pro tip, the ability concept.
Screenplay is not just for UI. Actors can have abilities. You can give an actor the ability to call an API or query a database. This allows you to mix UI and API testing seamlessly in the same flow. Actor attempts to call an API.get. Endpoint, click on button.
Scenario 3, the superclass anti-pattern.
A common mistake in framework design is treating inheritance as a mechanism for code reuse. Junior SDETs often create a base test class and dump everything into it: driver setup, reporting, database helpers, JSON parsers, and Excel readers. Every test class extends this base test. This creates a God class tightly coupling your tests to unrelated logic, making the framework brittle and impossible to maintain. Before code problem, the monolithic base test. Disclaimer, always test code in a non-production environment. This class violates the single responsibility principle. It is trying to be a driver manager, a report logger, and a database connector all at once. Any test extending this inherits all this weight, even if it does not need it. This is polluted interface design. A simple login test now has access to database methods and JSON parsers it should never touch. It makes the IDE autocomplete messy and hides dependencies.
The solution, composition over inheritance.
The architect's approach is to favor composition over inheritance. We break the base test apart. We use test listeners for the lifecycle opening or closing browsers, and static utility classes or dependency injection for helpers. The test class stays clean and only calls what it explicitly needs. After code solution, clean composition. Disclaimer, always test code in a non-production environment. We replaced extends base test with a listener. The test listener class handles the at before method and at after method logic behind the scenes. The test class itself is now a plain Java object, POJO with no parent dependency. We access the database via a specific database utils class. This is composition. We bring in functionality only when we need it, keeping the architecture modular and testable.
Follow-up 1. If we do not extend base test, where do we put common setup annotations like at before group or at before suite?
Answer, these should go into a dedicated test runner class or a global setup listener. In modern test NG or JUnit 5 frameworks, you can register global execution listeners that run once before the entire suite, completely decoupling configuration from the test logic.
Follow-up 2. Does not calling static methods like driver manager .getDriver parentheses make parallel execution harder?
Answer, not if the underlying implementation uses thread local. As we saw in scenario 1, if driver manager wraps a thread local WebDriver, calling the static getter is perfectly thread safe because it returns the specific instance for the current thread.
Follow-up curveball. How would you handle this in a language that does not support annotations or listeners the same way, like Python or PyDist?
Answer, in PyDist, we use conftest.py and fixtures. Instead of inheritance, we inject the driver fixture into the test function. This is effectively dependency injection, which is the functional equivalent of the composition pattern we just discussed for Java.
Pro tip, the rule pattern.
If you are using JUnit 4 or 5, look into rules or extensions. They allow you to plug in behaviors, like auto-retrying failed tests or capturing logs, without forcing your test classes to inherit from a specific parent. This keeps your hierarchy flat and flexible.
Scenario 4. Handling multi-tab flows.
Modern applications often open PDF reports, payment gateways, or help articles in new browser tabs. A common flakiness source is how automation handles this context switching. Junior engineers rely on hard-coded indexes, for example, switch to the second tab, which is unstable because the OS does not guarantee the order of window handles. We need a deterministic, criteria-based switching strategy. Before code problem, the index assumption. Disclaimer, always test code in a non-production environment. This is a race condition waiting to happen. If the browser is slow to open the tab, tabs.get1 throws an index out of bounds exception. Furthermore, Selenium does not guarantee that the new tab is always at index 1. It depends on the OS window manager. After closing the tab, the driver object is still pointing to the closed window handle. Any subsequent command will throw a no such window exception. The script effectively crashes here.
The solution, criteria-based switching.
The architect's approach is to switch based on page content, not window index. We iterate through available windows and switch only when we find a matching title or URL. We also preserve the original handle to ensure we can safely return to the main application. After code solution, dynamic window switching. Disclaimer, always test code in a non-production environment. First, we cache the current window handle. This is our safe harbor. No matter what happens during the switching logic, we know exactly where the main application is. We iterate through every open window and check its title. This makes the test robust. Even if 5 other pop-ups are open, we will find the specific one we care about based on its content.
Follow-up 1. What if the new tab takes 5 seconds to load its title?
Answer, this logic would fail if run immediately. To fix this, we wrap the getWindowHandles parentheses call in an explicit wait. We wait until expected conditions number of windows to be 2 or more is true before we start iterating. This ensures the browser has fully registered the new tab.
Follow-up 2. How do we handle this in parallel execution? Will not driver.getWindowHandles parentheses return windows from other tests?
Answer, no. And this is why scenario 1, thread local, is so important. Since driver is thread local, It effectively refers to a specific session ID on the Selenium grid. It can only see the windows associated with that specific session, so parallel tests remain completely isolated.
Follow-up curveball. What if the new window is not a browser tab, but a browser-level authentication pop-up, basic auth?
Answer: window handles will not work there because it is not a DOM object. It is an OS overlay. In Selenium 3, we used protected 8.8 F6C 633B 14469B 59 DF46 Phi 86 add 1B7 __. In Selenium 4, we use the DevTools protocol CDP, or the has authentication interface to register credentials before navigation, bypassing the pop-up entirely.
Pro tip, cleaning zombie windows.
When automating workflows that open many tabs, always use a try finally block in your test logic. In the finally block, verify that driver.getWindow handles (size == 1. If it is greater than 1, force close the extra tabs. This prevents zombie windows from eating up RAM on your execution grid node.
Scenario 5, the factory pattern.
As your test suite grows, you need to support multiple browsers: Chrome, Firefox, Edge, and execution modes, local, headless, Docker, cloud, grid. Junior engineers handle this by piling endless if-else statements into the setup parentheses method. This violates the open or closed principle. Every time a new browser version or capability is added, you risk breaking the core setup logic. Before code problem, the conditional spaghetti. Disclaimer: always test code in a non-production environment. This setup method is trying to do too much. It configures options, handles logic, and creates instances. If you want to add Safari, you modify this file. If you want to change Chrome arguments, you modify this file. This conditional logic becomes a maintenance bottleneck. It creates a rigid dependency where the test class knows too much about how browsers are created, rather than just asking for one.
The solution, the driver factory.
The architect's approach is to abstract creation logic into a factory pattern. The test class does not care how the driver is created. It just asks the factory for a driver. This centralizes browser configuration. If we need to update Chrome capabilities, we change it in one place, the factory, and it reflects across thousands of tests immediately. After code solution, centralized factory. Disclaimer: always test code in a non-production environment. The factory handles the decision logic. The complexity of choosing the right class, Chrome versus Firefox, is hidden here. The client test class simply calls driver factory.create instance. Chrome configuration is isolated. We extract the options setup into private helper methods. This keeps the code clean and allows us to have different configurations, for example, specific mobile emulation settings, managed neatly.
Follow-up 1. How does this integrate with the thread local pattern from Scenario 1?
Answer: they work together perfectly. In your driver manager from Scenario 1, instead of driverref.set new Chrome driver parentheses, you would call driverref.set driver factory.create instance, browser name. The factory creates the object, and thread local manages its thread safety.
Follow-up 2. What if I need to run tests on a remote grid, like Selenium Grid or Browser Stack, instead of locally?
Answer: you extend the factory. You add a check for an execution mode property, for example, remote equals true. If true, the factory returns a remote web driver, hub URL, capabilities, instead of a local driver. The test class remains 100% unaware of this switch.
Follow-up curveball. Why use a static factory instead of an abstract factory or supplier interface?
Answer: for simple setups, a static factory is sufficient. However, if the browser configurations are complex, for example, different profiles for different user roles, using a supplier WebDriver functional interface or an abstract factory is better because it allows for dependency injection and easier unit testing of the factory logic itself.
Pro tip, browser enums.
Avoid using raw strings like Chrome or Firefox in your switch statements. Create an enum browser type Chrome, Firefox, Edge. This eliminates typo-related bugs like typing Chrome instead of Chrome at compile time rather than runtime.
Scenario 6, Dependency Injection, State Sharing.
A major architectural challenge in BDD Cucumber, or complex test NG workflows, is sharing state between steps. You create an order in step 1, and you need that order ID in step 5 to verify the DB. Junior engineers solve this by dumping data into a global static map. This creates a state leak, where data from test A bleeds into test B during parallel execution, causing random failures. Before code problem, the static data dump. Disclaimer: always test code in a non-production environment. This static map is shared across the entire JVM. If two tests run in parallel threads, they both write to run data. Thread A overwrites the current order ID of thread B, causing thread B to verify the wrong order. This creates rigid coupling. The validation steps class now implicitly depends on the order steps class running first and populating this specific string key. It is fragile and typo-prone.
The solution, Dependency Injection, Pico Container.
The architect's approach is constructor injection. We create a dedicated test context POJO, plain old Java object, to hold the state. We use a die container, like Pico Container in Cucumber, to automatically create one instance of this context per scenario and inject it into every step definition class that needs it. After code solution, context injection. Disclaimer: always test code in a non-production environment. This is our world object. It lives only as long as the test scenario lives. It is strongly typed string order ID, avoiding the messy casting of a hash map. This is the magic. We do not say new test context parentheses. The framework Pico Container sees that order steps needs test context, creates it, and passes it in. It passes the exact same instance to validation steps, ensuring they share data safely.
Follow-up 1. Does this work for parallel execution?
Answer: yes, perfectly. The die container creates a new instance of test context for every single scenario execution thread. Thread A has context A, and thread B has context B. They are completely isolated in memory.
Follow-up 2. Can I use this for the WebDriver too?
Answer: absolutely. Just as we injected test context, we can wrap the WebDriver in a driver manager class and inject that into the step definitions. This removes the need for any static driver references anywhere in your code.
Follow-up curveball. What happens if I create a new instance using new test context parentheses inside the step definition manually?
Answer: you break the pattern. If you manually say new test context parentheses, you are creating a local orphan object that no other class knows about. You must let the container pass the instance through the constructor to ensure all classes share the same object reference.
Pro tip, domain-specific contexts.
Do not create one giant test context file with 500 variables. Split them up. Create customer context, order context, and payment context. You can inject multiple contexts into a single step definition class, public mySteps, customer context CC, order context awk. This keeps your state objects small and relevant.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem solving, generally most asked, and system design. Required for your software testing, job interviews like automation test engineer jobs, QA analyst jobs, performance test engineer jobs, API tester jobs, playwright automation test engineer jobs, DevOps test engineer jobs, automation test architect jobs, mobile application test engineer jobs, SDET, tester jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes real-world problem-solving interview questions and answers where almost 80% of the people are failing to answer, scenario-based questions and answers, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section. These questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 6 PDFs in a single zip file from below given links.
That concludes framework architecture. We have moved from static variables to thread local, swapped POM for screenplay, and implemented dependency injection. Your framework skeleton is now solid, scalable, and thread-safe. But a perfect skeleton is useless if the tests themselves fail randomly.
Category 2, reliability, flakiness, and synchronization.
This is where the battle is won or lost. Flakiness, tests that pass today but fail tomorrow, destroys trust in automation. In this section, we tackle the hardest synchronization challenges: React or Angular DOM updates, asynchronous events, self-healing locators, and visual regression. We aren't just adding weights, we are architecting stability.
Scenario 7, the stale element reference nightmare.
In modern single-page applications, React, Vue, Angular, the DOM updates asynchronously. You find an element, but before you click it, the JavaScript framework refreshes that part of the page. The ID is the same, the location is the same, but the reference is dead. Selenium throws a stale element reference exception. Junior engineers fix this with hard sleeps or try-catch loops inside every test method. Before code problem, the brittle retry. Disclaimer: always test code in a non-production environment. This pattern clutters the test logic. Every single interaction needs this boilerplate try-catch block. It is unreadable and violates DRY. Do not repeat yourself. The hard sleep slows down the suite. If the element recovers in 100 milliseconds, you still wait 2 seconds. Over 1,000 tests, this adds hours to the execution time.
The solution, the smart wrapper, functional wait.
The architect's approach is to wrap interactions in a fluent wait that specifically ignores stale exceptions. We create a generic click method that accepts the by locator, not the web element. This forces the driver to refine the element fresh from the DOM every time it retries, guaranteeing a live reference. After code solution, robust interaction wrapper. Disclaimer: always test code in a non-production environment. We explicitly tell the wait object, if you see a stale element reference exception, do not fail. Treat it as if the element is not ready yet and try again. This Lambda function is key. By passing the locator by, instead of the element web element, d.findElement executes fresh on every polling interval, every 500 milliseconds. It automatically reacquires the element from the DOM until it successfully clicks.
Follow-up 1, does this pattern work with the page factory at find by annotation?
Answer: yes, but you have to be careful. Page factory creates proxy elements. If you use @cache lookup, the element is found once and cached. If the DOM changes, @cache lookup will cause stale element exceptions that even this wrapper might struggle with. For dynamic apps, avoid @cache lookup.
Follow-up 2, what if the element is stale because it was actually removed from the page permanently?
Answer: the fluent wait handles this gracefully. It will keep polling and retrying for the duration of the timeout, for example, 10 seconds. If it never reappears or stays stale, it throws a timeout exception with a clear message, which is a valid failure.
Follow-up curveball, why use a by locator instead of a web element in the method signature? Why is that distinction critical?
Answer: because a web element is a snapshot in time. Once created, it is tied to a specific node in the DOM. If the DOM refreshes, that object becomes garbage. A by locator is just a recipe for how to find the element. Passing the recipe allows us to bake a fresh element every time.
Pro tip, the JavaScript click fallback.
Sometimes, stale element reference happens because an element is covered by a translucent loading spinner that disappears instantly. If the standard click fails consistently, you can enhance the wrapper to fall back to JavaScript executor.execute script, argument 0. Click parentheses, element. This forces the click event directly on the DOM node, bypassing some standard Selenium visibility checks.
Scenario 8, smart waits versus hard sleeps.
One of the biggest causes of slow test execution is the abuse of thread.sleep parentheses. When testing asynchronous backend processes, like generating a PDF report, sending an email, or processing a payment. Junior engineers guess how long it will take and hard code a sleep, for example, 30 seconds. If the process takes 5 seconds, you waste 25 seconds. If it takes 31 seconds, the test fails. We need a polling strategy. Before code problem, the guesswork sleep. Disclaimer: always test code in a non-production environment. This hard sleep destroys test performance. In a suite of 500 tests, if every test has just one unnecessary 5-second sleep, you add 40 minutes to the execution time. It also makes the test brittle. A slight network lag causes a failure even if the app is working.
The solution: awaitility polling.
The architect's approach is to use a dedicated polling library like awaitility or custom fluent waits. Instead of sleeping, we explicitly define a condition, for example, file exists, database status is complete. We poll this condition at regular intervals, for example, every 1 second. The moment it becomes true, the test proceeds immediately. After code solution, smart polling. Disclaimer: always test code in a non-production environment. We define the boundary. We wait at most 30 seconds, but we check every single second. This makes the test dynamic. It handles the worst-case scenario while optimizing for the best-case scenario. We provide a Lambda function as the exit condition. As soon as this returns true, the wait breaks. This ensures the test runs exactly as fast as the application allows. Zero wasted time.
Follow-up 1. Cannot we just use Selenium's implicit wait for everything? Why do we need explicit or fluent waits?
Answer: implicit wait is global and applies to all element searches. It does not work for non-web element conditions, like file downloads or DB updates. Worse, mixing implicit and explicit waits causes unpredictable timeout behavior because they can compound each other.
Follow-up 2. Does polling too frequently, for example, every 10 milliseconds, hurt performance?
Answer: yes. If your polling condition involves a heavy operation, like an API call or DB query, polling too fast can DDoS your own test environment or spike the CPU. You must choose a poll interval that balances responsiveness with system load.
Follow-up curveball. How do you debug a timeout exception when using these waits in a headless CI/CD pipeline?
Answer: standard logs aren't enough. You need to implement an on-failure hook. When a wait times out, the framework should automatically take a screenshot, capture the page source, HTML, and dump the browser console logs, JavaScript errors. This context is critical for understanding why the wait failed.
Pro tip: disable CSS animations.
Often, waits fail because an element is present but not clickable due to a fading animation. In your base test setup, inject JavaScript to disable jQuery or CSS animations. jQuery.fx.off equals true. This makes the UI snap instantly to the final state, making your waits more reliable and tests faster.
Scenario 9. Self-healing locators.
Modern front-end frameworks, like React or Angular, often generate dynamic element IDs, for example, button size 123, that change on every deployment. Junior engineers write tests that rely on these brittle attributes, causing the suite to fail whenever developers push code. The architect's solution is self-healing automation, a mechanism that automatically tries alternative strategies when the primary locator fails. Before code problem, brittle locators. Disclaimer: always test code in a non-production environment. This test is doomed. The ID 98273 is likely a hash generated by the Webpack compiler. Tomorrow it will be submit BTN 55102, and the test will fail, requiring manual maintenance.
The solution: the multi-locator strategy.
Real self-healing involves a I like Helenium, but you can architect the pattern in vanilla code. We create a smart finder that accepts a primary locator, the ID, and a list of backup locators, CSS class XPath text. If the primary fails, the framework iterates through the backups, finds the element, logs a warning suggesting an update, and keeps the test alive. After code solution, fallback logic. Disclaimer: always test code in a non-production environment. We assume the best case first. If the primary locator works, we proceed immediately with zero performance cost. If the primary fails, we do not crash. We enter the healing loop. We try CSS selectors, text matches, or relative locators. If any of them work, the test passes and the logs tell us exactly which locator saved the day.
Follow-up 1. Does not trying multiple locators slow down the test execution?
Answer: only when the test is already failing. On the happy path, when the primary ID works, there is zero performance penalty. The extra time is only spent during the failure scenario, which is acceptable because the alternative is a broken build.
Follow-up 2. How do we ensure we fix the broken primary locator eventually?
Answer: that's why logging is crucial. In the solution code, we print healed using. In a real framework, we would tag the test report with a healed warning status. This alerts the SDETs to update the primary locator in the next maintenance cycle, rather than dealing with an emergency failure.
Follow-up curveball. What is the risk of false positives with self-healing?
Answer: the risk is finding the wrong element. If your backup locator is too generic, for example, by .tag name, button, the script might click the cancel button instead of submit. To mitigate this, backup locators must still be specific, for example, matching button text or surrounding attributes.
Pro tip: AI integration.
While you can code basic fallback logic manually, look into tools like Selenium. It wraps the standard Selenium driver and uses machine learning to compare the current page DOM against the last known successful DOM state to find the element, even if IDs, classes, and positions have all changed.
Scenario 10. Handling toast messages.
Toast messages, temporary pop-ups like saved successfully, are notorious for causing flaky tests. They appear for only 2 to 3 seconds and then vanish from the DOM. Junior engineers often miss them because the script checks too late, or they fail because the script tries to interact with them while they are fading out. We need a strategy to catch them instantly. Before code problem, the race condition. Disclaimer: always test code in a non-production environment. This is a timing gamble. If the backend is slow to confirm the save, the toast has not appeared yet, and find element throws an exception immediately. If the test machine is slow, the toast might have already faded away before this line executes.
The solution: explicit visibility wait.
The architect's approach is to explicitly wait for the visibility of the element. We do not just check if it exists. We tell the driver to halt until the toast is rendered and visible. Crucially, we grab the text immediately, because the element might be destroyed milliseconds later. After code solution, synchronized capture. Disclaimer: always test code in a non-production environment. This is the net. We wait up to 5 seconds for the toast to appear. The moment it hits the screen, the driver grabs the reference. This handles network lag perfectly. This is a state cleanup step. Before moving to the next test step, like clicking another button, we ensure the toast is gone so it does not overlap or obscure other UI elements, preventing element click intercepted exception.
Follow-up 1. What if there are multiple toast messages stacking on top of each other?
Answer: you change the strategy to visibility of all elements located by. This returns a list of web elements. You can then iterate through the list to verify that all expected messages, for example, file uploaded, email sent, are present in the stack.
Follow-up 2. The toast message uses a CSS animation to slide in. Selenium says it is not visible during the animation. How do we fix this?
Answer: this is tricky. Selenium checks for opacity and size. If it fails, switch to checking expected conditions. Presence of element located. This confirms the element is in the DOM, even if the animation makes it technically invisible to the user for a split second.
Follow-up curveball. What if the toast message is inside a shadow DOM component?
Answer: standard locators will not work. You need to use the getShadowRoot method, Selenium 4. First, locate the host element, call getShadowRoot, and then find the toast inside that shadow root context. Alternatively, use a deep CSS selector if supported by the browser.
Pro tip: verify content, not just presence.
Never just check is displayed parentheses. Always assert the text content, assert equals, get toast message success. A toast saying error, save failed is also displayed, and checking only for visibility would give you a false positive pass on a critical bug.
Scenario 11. The retry controversy.
Test flakiness is the enemy of CI/CD. To combat this, test NG and JUnit offer auto retry mechanisms. Junior engineers implement a global retry listener that blindly reruns every failed test 3 times. While this turns the pipeline green, it masks critical performance issues and race conditions, effectively hiding bugs under the rug. Before code problem, blind retries. Disclaimer: always test code in a non-production environment. This logic is dangerous. If a test fails because of an assertion error, for example, expected $100 but found $50, retrying it 3 times will not fix the bug. It just wastes CPU cycles. We are treating logic bugs the same as infrastructure blips.
The solution: context-aware retry logic.
The architect's approach is selective retrying. We inspect the cause of the failure. If it is an infrastructure issue, timeout, stale element, network, we retry. If it is a logic failure, assertion error, we fail immediately. This ensures we catch bugs fast while being resilient to environment instability. After code solution, intelligent retry. Disclaimer: always test code in a non-production environment. If the business logic is wrong, retrying is pointless. We fail fast to give feedback to the developer immediately. These exceptions indicate environment instability. The test logic might be correct, but the browser or network blinked. This is the only valid scenario for a retry.
Follow-up 1. In the reporting dashboard, retried tests show up as skipped or flaky. Does this mess up the pass percentage?
Answer: yes. Standard reporters, like test-ng default, show the failed attempts as skipped. To fix this, you must implement an iTest listener. In unfinished parentheses, iterate through the results and remove the skipped entries if a subsequent retry passed, ensuring the final report shows only the definitive result.
Follow-up 2. Does not retrying hide the fact that our environment is unstable?
Answer: it can. That's why we do not just retry silently. We log a specific warning, unstable test passed on retry number 2. We then use a dashboard metric to track flakiness rate. If a test is retried in greater than 20% of builds, it gets quarantined and fixed, rather than just ignoring it.
Follow-up curveball: a test creates a user in the DB. It fails at the end, you retry it. What happens?
Answer: the retry fails immediately with a duplicate user error because the first run did not clean up. Retries require idempotency. Your before method must check if data exists and clean it, or the test data generation must create a unique ID, for example, timestamp, for every single run, including retries.
Pro tip: Docker and retries.
If you are using Dockerized Selenium, Selenoid, or Xaleneum, you do not need code-level retries for browser crashes. These tools have video recording and live preview. Instead of retrying blind, check the video artifact. Often, a crash is actually the container running out of memory, which a code retry will not fix. You need to increase container resources.
Scenario 12. Visual regression integration.
Selenium checks functionality, not aesthetics. A button can work perfectly even if it overlaps text or is invisible due to white-on-white CSS. Junior engineers try to solve this by taking screenshots and performing bit-by-bit pixel comparison. This is extremely brittle. A 1px rendering shift by the browser causes the entire test to fail. Before code problem, manual pixel comparison. Disclaimer: always test code in a non-production environment. This approach is flawed because browsers render pixels differently depending on the OS, GPU, and driver version. A valid UI update often triggers a false positive failure because the anti-aliasing changed slightly.
The solution: AI-powered visual testing.
The architect's approach is to delegate visual checking to a specialized tool like Applitools Eyes or Percy. These tools use visual AI to ignore minor rendering noise and focus on actual layout changes. We integrate this into the Selenium code with a single line, treating the visual check as just another assertion. After code solution, Applitools integration. Disclaimer: always test code in a non-production environment. Instead of manual comparisons, we send the DOM and screenshot to the visual AI cloud. The tool handles dynamic content, stitching scrolling pages, and ignoring noise like blinking cursors.
Follow-up 1. How do you handle dynamic content, like a date or timestamp or a random advertisement?
Answer: visual testing tools allow you to define ignore regions or layout regions. We programmatically annotate the dynamic elements, for example, eyes.check, target dot window parentheses dot ignore by dot ID clock, so the AI knows to skip comparing pixels in that specific area.
Follow-up 2. Does not sending screenshots to the cloud slow down the execution?
Answer: it can. To mitigate this, we use the visual grid or ultra-fast grid pattern. Instead of sending an image, the local runner captures the DOM or CSS snapshot and sends that to the cloud, which is tiny. The cloud then renders the page in 50 different browser resolutions in parallel instantly.
Follow-up curveball. If the UI changes intentionally, new feature, the test fails. How do you maintain the baseline without rerunning everything?
Answer: visual testing tools have a dashboard workflow. When a test fails due to a valid UI change, you log into the dashboard and click Accept New Baseline. This updates the reference image for all future runs. You do not change a single line of code.
Pro tip, component-level testing.
Do not just test full pages. If you use Storybook for React or Angular, integrate visual testing there. Validating individual components, buttons, cards, in isolation catches 80% of visual bugs before they ever reach the Selenium integration suite. We have now stabilized the execution layer. Our tests handle weights, dynamic locators, and visual glitches. But a stable test is useless if the data it relies on is broken. This brings us to the most complex part of enterprise automation: data management.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your software testing, job interviews like automation test engineer jobs, QA analyst jobs, performance test engineer jobs, API tester jobs, playwright automation test engineer jobs, DevOps test engineer jobs, automation test architect jobs, mobile application test engineer jobs, SDET, tester jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes real-world problem-solving interview questions and answers where almost 80% of the people are failing to answer, scenario-based questions and answers, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 6 PDFs in a single zip file from below given links.
Category 3, Test Data Management, TDM and State.
Hard-coded data is the #1 killer of parallel execution. If test A deletes a user that test B tries to log in with, you have a collision. In this section, we move from static Excel sheets to dynamic API injection, database mocking, and state hydration. We treat data as infrastructure.
Scenario 13, the burn data dilemma.
When running tests in parallel, shared data causes collisions. Scenario: Test 1 changes a product's price to $50. Test 2 expects the price to be $100. Both are running at the same time. Test 2 fails not because of a bug but because of burned data. Junior engineers solve this by creating huge static lists of users, user 1, user 2, which eventually run out. Before code problem, hard-coded data dependencies. Disclaimer: always test code in a non-production environment. This SKU exists in the database, but its inventory count is a shared state. If 5 tests run in parallel and buy this item, the inventory hits 0, and the 6th test fails without of stock.
The solution, just-in-time JIT data creation.
The architect's approach is to create data fresh for every single test execution using APIs. We do not rely on existing data, we manufacture it. Before the UI test starts, we call a backend a PI to create a unique user and a unique product with infinite stock. The test runs in a completely isolated data bubble. After code solution, a PI-driven setup. Disclaimer: always test code in a non-production environment. The user factory hits the backend a PI, for example, post/a PI or users, and returns a brand new user object with a random email, for example, test_82736@mail.com. This user has never been touched by any other test. We even create the product on the fly. This ensures the inventory is fresh and the price is exactly what we assert, eliminating any chance of external interference.
Follow-up 1. Does not creating data via a PI slow down the test?
Answer: marginally, but the stability gain is worth it. A PI calls take milliseconds. UI interactions take seconds. Adding 200 milliseconds of a PI setup to prevent a 5-minute debug session for a false positive is a massive ROI win.
Follow-up 2. What about cleaning up this data? Will not the database get bloated?
Answer: yes. We use the teardown pattern. The user factory tracks every ID it creates. In the add-after method, we iterate through that list and fire delete/a PI or users/ID calls to clean up the environment immediately after the test finishes.
Follow-up curveball. We are testing a legacy system with no APIs. We can only create data via SQL. How do we handle parallel TDM?
Answer: you use the data pool pattern. You pre-generate 1,000 records in the SQL DB before the suite starts. You push these IDs into a thread-safe queue, like concurrent linked queue. Each test pops a unique ID from the queue to use. This ensures no two tests grab the same record.
Pro tip: Faker library.
Use libraries like Java Faker or Data Faker to generate the random data. Instead of user 1, user 2, you generate real-looking data like John Smith, 123 Maple Drive. This often uncovers edge case bugs, for example, names with apostrophes like O'Connor, that simple test data misses.
Scenario 16. State hydration, redux, or Vuex injection.
Testing a step 5 in a wizard is painful. You usually have to automate steps 1 through 4, which takes time and creates points of failure. Junior engineers automate the clicks. Architects use app state hydration. If the frontend uses redux, Vuex, or local storage, we can inject the desired state directly into the browser's memory, teleporting the user instantly to step 5. Before code problem, the UI marathon. Disclaimer: always test code in a non-production environment. This is a domino effect test. A bug in the address validation logic prevents us from ever knowing if the summary page works. This reduces test coverage for downstream features and drastically increases execution time.
The solution: JavaScript state injection.
The architect's approach relies on the JavaScript executor. Most modern single-page applications, SPA, store their state in a global object, like window.store for Redux. We can execute a JavaScript command to update this object directly, forcing the UI to render step 5 immediately without clicking a single button. After code solution, Redux dispatch. Disclaimer: always test code in a non-production environment. We bypass the UI entirely. By dispatching an action directly to the Redux store, the application reacts as if the user had manually filled out the previous 4 steps. This reduces a 2-minute setup to a 50 milliseconds execution.
Follow-up 1. What if the application exposes the store only in dev mode and not production?
Answer: this is common. In production builds, React or Angular minifies code and hides global variables. To fix this, you ask developers to expose the store on window object conditionally. If window.cypress or window.selenium, window.store equals store. This creates a testability hook only available when automation is running.
Follow-up 2. Can we do this with local storage or session storage?
Answer: yes, and it is even easier. js.execute script, window.localstorage.setItem, user token size. Many apps read from local storage on reload. So you set the item, then call driver.navigate /refresh and the app loads in the authenticated state.
Follow-up curveball. Injecting state works, but the UI looks broken because the CSS did not load properly. Why?
Answer: this happens when the state relies on a sync data fetching that you skipped. If Step 5 expects images loaded in Step 1, injecting Step 5 state might result in missing assets. You must ensure your injected payload includes all necessary dependencies, effectively mocking the result of those previous network calls.
Pro tip, security policy, CSP.
Sometimes execute script fails because of a strict content security policy, CSP, that blocks inline scripts. You may need to configure your WebDriver capabilities to disable CSP checks, disable web security and Chrome options in the test environment to allow this injection magic.
Scenario 17. Mocking third-party dependencies.
Your application integrates with Stripe for payments or Twilio for SMS. Testing against their real sandbox APIs is slow, rate-limited, and requires internet access. If Stripe goes down, your deployment pipeline fails. Junior engineers use the real sandbox. Architects use WireMock to simulate these external services. Before code problem, dependency on external vendor. Disclaimer: always test code in a non-production environment. By relying on the real Stripe sandbox, you introduce an external point of failure. Your CI/CD pipeline now requires a working internet connection and valid Stripe credentials, creating brittle tests.
The solution, WireMock, service virtualization.
The architect's approach is to mock the external service. We point our application to a local WireMock server instead of a pi.stripe.com. We tell WireMock exactly what to return: success, declined, timeout. This gives us full control over the test scenarios and instant, offline responses. After code solution, WireMock stubbing. Disclaimer: always test code in a non-production environment. We program the mock server. We say, if the app tries to post a /v1/charges, do not actually process money. Just instantly return a 402 error. This allows us to test edge cases, declines, timeouts that are hard to reproduce with real cards. For this to work, the application under test out must be configured to point to localhost 8080 WireMock instead of the real Stripe URL. This is usually done via config files in the CI environment.
Follow-up 1. Does WireMock support HTTPS? Our app refuses to connect to http://localhost.
Answer: yes, WireMock supports HTTPS. However, since it uses a self-signed certificate, your browser or app will reject it. You must configure your Selenium WebDriver to set accept insecure certs, true, and configure your backend Java or Node process to trust the WireMock key store.
Follow-up 2. Is not there a risk that the mock falls out of sync with the real API?
Answer: yes, this is drift. If Stripe changes their API schema but your mock stays the same, your tests pass but production fails. To fix this, you use contract testing, packed, or occasionally run a live suite against the real sandbox to validate the mocks.
Follow-up, curveball. Can WireMock simulate a slow network to test our app's timeout logic?
Answer: absolutely. You can add, with fixed delay, 5,000 to the stub. This forces WireMock to wait 5 seconds before responding, allowing you to verify if your application correctly shows a connection timed out message to the user.
Pro tip, record and playback.
You do not have to write stubs manually. WireMock has a record mode. You run it as a proxy, click through your app once hitting the real API, and WireMock records all requests/responses. You then switch to playback mode, and it replays those responses forever without hitting the internet. That concludes test data management. We have moved away from brittle UI creation and hard-coded data to API injection, database verification, state hydration, and service virtualization. Now that we have stable tests and stable data, we need to scale. How do we run this in a pipeline? Let's move to Category 4, CI/CD and DevOps integration.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem solving, generally most asked, and system design. Required for your software testing job interviews like automation test engineer jobs, QA analyst jobs, performance test engineer jobs. API tester jobs, Playwright automation test engineer jobs, DevOps test engineer jobs, automation test architect jobs, mobile application test engineer jobs, SDET, tester jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes real-world problem-solving interview questions and answers where almost 80% of the people are failing to answer. Scenario-based questions and answers. System design questions and answers where almost 90% of the people are failing to answer. With detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 6 PDFs in a single zip file from below given links.
Category 4, CI/CD and DevOps integration.
Automation that lives on a laptop is useless. To add value, tests must run in the pipeline, block bad code, and provide feedback instantly. In this section, we stop thinking like testers and start thinking like DevOps engineers. We cover pipeline strategy, Dockerized grids, and environment orchestration.
Scenario 18, the 15-minute feedback loop.
A full regression suite takes 10 hours. Developers cannot wait 10 hours for a pull request PR check. Junior engineers try to solve this by running everything overnight, finding bugs 24 hours too late. The architect's solution is test segmentation. We slice the suite into smoke, critical path, and regression layers, ensuring the PR gets a go/no-go decision in under 15 minutes. Before code problem, the monolithic run. Disclaimer, always test code in a non-production environment. This configuration treats every test as equal. It runs the critical checkout test, high value, and the trivial footer link test, low value, in the same run. This bloat makes the feedback loop impossibly slow for active development.
The solution, tagging and parallelism.
The architect's approach uses annotation tagging groups and parallel execution. We verify the critical paths with @test, groups equals smoke, and configure the CI runner to execute only these tests, highly parallelized for PR checks. The full suite is reserved for nightly runs. After code solution, targeted execution. Disclaimer, always test code in a non-production environment. We aggressively parallelize at the method level. With 10 threads, a suite that usually takes 30 minutes can theoretically finish in 3 minutes, assuming thread-safe code, scenario 1. We strictly filter by group. We include smoke for confidence and explicitly exclude flaky tests to prevent false alarms from blocking a deployment.
Follow-up 1. Who decides which tests are smoke and which are regression?
Answer, this is a collaborative decision. Smoke tests cover the money paths, login, add to cart, checkout. If these break, the business stops. Regression covers edge cases and field validations. As an architect, I enforce a rule: smoke tests must be 100% stable. If a smoke test flakes, it is demoted to regression until fixed.
Follow-up 2. Can we automate the selection of tests based on which files changed in the PR?
Answer, yes. This is called predictive test selection. Tools like Launchable or custom scripts analyze the git diff. If cart service.java changed, the system intelligently selects only the tests mapped to the cart module, reducing execution time further.
Follow-up curveball. We have 10 threads but only one database. How do we prevent 10 smoke tests from colliding on data?
Answer, this goes back to scenario 13, TDM. Parallelism requires data isolation. Each of the 10 threads must use the IPI to generate its own unique user and order data before execution. If you share a single static user across 10 threads, parallelism will fail immediately.
Pro tip, fail fast.
Configure your test NG or JUnit runner with a fail fast listener. If the first 5 tests in a PR check fail, stop the entire run immediately. There is no point in waiting 10 minutes to see the other 95 failures. Give the feedback to the developer instantly.
Scenario 19. Dockerized execution grids.
Maintaining a static Selenium grid, a hub and fixed nodes, is an operational nightmare. Browsers auto-update and break drivers, nodes freeze and sessions hang. Junior engineers waste hours restarting servers. The architect's solution is ephemeral infrastructure. We spin up a fresh, disposable Docker container for the browser per test run and destroy it immediately after.
The solution: test containers, infrastructure as code.
The architect's approach is to manage infrastructure inside the code using a library like test containers. We define the browser container in Java. When the test starts, it pulls the Docker image, starts the container, runs the test, and then nukes the container. We get a pristine environment every single time. After code solution, ephemeral containers. Disclaimer: always test code in a non-production environment. This logic is powerful. The test itself controls its infrastructure. It demands a specific version of Chrome. Docker handles the download and startup. No manual sysadmin work required. We get a driver connected to this specific, isolated container. Even if another test running in parallel crashes its browser, this test is unaffected because they are in totally separate containers.
Follow-up 1. Does not pulling a Docker image for every test make it slow?
Answer: it would, but test containers caches the image locally after the first pull. Starting a container takes only 1 to 2 seconds. The stability gained from having a clean session far outweighs this negligible startup cost.
Follow-up 2. Can we see what's happening inside the container during execution?
Answer: yes. With Selenoid or test containers, you can enable VNC recording. The container will stream a live video of the browser execution to a port or save an MP4 file after the test finishes, which is perfect for debugging failures.
Follow-up curveball. Your Jenkins agent is Linux, but your application requires Internet Explorer/Safari testing. Can Docker help?
Answer: no. Docker containers share the host kernel Linux. You cannot run native Safari, Mac OS, or IE Windows in a standard Linux Docker container. For those browsers, you must route traffic to a cloud provider, Browser Stack or Sauce Labs, or a specific Windows or Mac VM node in your grid.
Pro tip: Selenium/Selenoid.
For enterprise scale, look at Selenoid. It is a Go-based implementation of Selenium Grid that spins up containers instantly on demand. It consumes 10 times less memory than standard Selenium Grid Java hubs and provides video recording out of the box.
Scenario 20. Handling CAPTCHAs and MFA and CI/CD.
A common deployment blocker is security. The application works fine locally, but in the CI/CD pipeline, the test fails because it hits a CAPTCHA or a multi-factor authentication (MFA) prompt. Junior engineers try to solve this with hacks like using image recognition to click CAPTCHA boxes. This is brittle, slow, and unreliable. Architects negotiate a proper testability hook with the security team. Before code problem, the UI hack. Disclaimer: always test code in a non-production environment. Using optical character recognition, OCR, is the wrong approach. You are trying to break the very feature you are testing. It is a constant maintenance battle against the security team.
The solution: the testability backdoor.
The architect's approach is to disable security features in non-production environments. We work with developers to create a test mode. When the application detects it is running in the CI/CD environment, via an environment variable or IP whitelist, it completely bypasses the CAPTCHA and MFA logic. After code solution, conditional bypass. Disclaimer: always test code in a non-production environment. The application itself is aware of its environment. The CI runner, Jenkins or GitLab, injects CI_mode equals true into the server's environment variables. The CAPTCHA validation is now conditional. It only runs if the test environment flag is false. For our automation scripts, this entire block is skipped, and the login proceeds instantly.
Follow-up 1. What about MF or OTP? How do we bypass a one-time code sent to a phone?
Answer: you use a pre-shared key. The backend is configured to accept a static OTP, for example, 0000000, only for whitelisted test users. Production users still go through the real SMS or authenticator flow, but automation uses a predictable backdoor.
Follow-up 2. The security team refuses to disable these features in the Q environment. What now?
Answer: this is a risk negotiation. The architect's role is to explain the cost of not having a bypass, slow, flaky tests, low coverage, versus the risk. A compromise is to have the bypass enabled only on a DevOps environment running on a private network, and run a smaller set of smoke tests on the secure Q environment.
Follow-up, curveball. How do we test the CAPTCHA feature itself to make sure it is working?
Answer: you do not test the CAPTCHA ability to block bots. That's Google's job if you use reCAPTCHA. You test your integration with it. You run one test that does not provide the bypass header and assert that the login is correctly blocked. This verifies your gate is working without trying to solve the puzzle.
Pro tip, the magic header.
Instead of environment variables, use a magic header. The CI runner injects X automation bypass, true. The application's API gateway or middleware checks for this header and disables security rules for that specific request only. This is more flexible and does not require restarting the server with new environment variables.
Scenario 21. Dynamic environment testing.
An enterprise has multiple environments: dev, QA, staging, UAT. Junior engineers create separate test suites for each, or worse, hardcode the URL. If a test is updated for the dev suite, they forget to update it for staging. The architect's solution is a single, unified test suite that can be dynamically pointed to any environment using external configuration. Before code problem, hard-coded URLs. Disclaimer: always test code in a non-production environment. This is not scalable. It requires a separate Git branch, release, or staging just to change the URL. It is error-prone and creates a maintenance nightmare when managing tests across 5 different environments.
The solution, externalized configuration.
The architect's approach is to treat configuration as code. We use property files, properties, YAML, for each environment. The code reads the target URL, username, and password from these external files. The CI/CD pipeline decides which file to use at runtime. After code solution, properties factory. Disclaimer: always test code in a non-production environment. The environment is a parameter passed from the outside, for example, Jenkins. If no parameter is passed, it defaults to QA. The code is no longer responsible for knowing where it is running. Based on the parameter, we load the correct file. env equals staging load staging.properties. This allows us to have different users, passwords, and API keys for each environment managed securely.
Follow-up 1. How do we pass this denv equals staging parameter from a Jenkins pipeline?
Answer: in your Jenkins file or Maven or Gradle command, you add it as a JVM argument. For Maven, the command would be mvn clean install denv equals staging. Jenkins can even provide a drop-down parameter for the user to select the target environment.
Follow-up 2. Should passwords be stored in these properties files?
Answer: no. Properties files are checked into Git, so they should not contain secrets. Passwords should be read from a secure vault, like HashiCorp Vault, a WS Secrets Manager, or injected as masked environment variables directly by the CI/CD tool.
Follow-up curveball. The staging environment is an exact replica of production, but the test data is different. How do we manage this?
Answer: you use role-based configuration. You can have a staging admin.properties and a staging read-only.properties. Your test runner can be configured to use a specific role file, allowing you to run different test suites with different permissions against the same environment.
Pro tip, owner res or Spring profiles.
For enterprise Java frameworks, use a mature library like Owner or Spring Profiles. Instead of manually loading files, you define an interface at config.sources, classpath, $env properties. And the library automatically maps properties to Java methods. This is cleaner and less error-prone.
Scenario 22, the tagging strategy.
As the suite grows, you need more granular control than just smoke versus regression. You need to run tests based on feature at feature, checkout, risk level at severity, critical, or type at tag, IPI. Junior engineers try to manage this by creating hundreds of separate test ng.xml files. Architects use a dynamic tagging strategy. Before code problem, XML file hell. Disclaimer, always test code in a non-production environment. This is unscalable. If a product manager asks for all critical checkout tests, but no flaky ones, you have to create a brand new XML file with complex include or exclude logic. This quickly becomes an unmanageable mess.
The solution, dynamic tag expressions.
The architect's approach is to use a single, generic XML file and pass in tag expressions from the CI/CD pipeline. Modern runners, test ng JUnit 5, PyTest can parse complex Boolean logic like smoke and checkout, and not flaky. After code solution, tag annotations. Disclaimer, always test code in a non-production environment. We decorate each test with rich metadata. This test belongs to multiple groups and has a severity and feature. This allows for powerful, multi-dimensional slicing. The CI/CD pipeline is now the brains. We can construct any combination on the fly. This gives the DevOps team and product managers the flexibility to create custom test runs without ever touching the codebase.
Follow-up 1. What is the difference between test ng groups and allure annotations like at severity?
Answer, groups are for execution control, which tests to run. Annotations are for reporting and analytics, how to categorize the results. You can filter your Allure report to see all critical tests, even if some were not executed in that specific run.
Follow-up 2. How does this relate to BDD frameworks like Cucumber?
Answer, it is the same concept. In Cucumber, you use tags at the top of your feature files, for example, @smoke at checkout. Your Cucumber runner options can then be configured to run specific tag expressions.
Follow-up curveball. A test is tagged @flaky but also @critical. Should it run in the PR check?
Answer, no. The PR check expression should be critical and not flaky. A critical test that is unstable provides zero value in a fast feedback pipeline. It just blocks developers. It should be quarantined and fixed immediately.
Pro tip, tag inheritance.
You can place tags at the class level. If you put @test, groups equals checkout, at the top of your checkout tests.java class, all 50 test methods inside that class will automatically inherit the checkout tag. This keeps your code DRY. That concludes CI/CD integration. We now have a fast, stable, and scalable execution strategy. We can run the right tests at the right time in a clean environment. But what happens when we move from monolithic apps to modern, distributed systems? This brings us to Category 5, microservices and modern architecture.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your software testing, job interviews like automation test engineer jobs, QA analyst jobs, performance test engineer jobs, API tester jobs, playwright automation test engineer jobs, DevOps test engineer jobs, automation test architect jobs, mobile application test engineer jobs, SDET, tester jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes real-world problem-solving interview questions and answers where almost 80% of the people are failing to answer, scenario-based questions and answers, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 6 PDFs in a single zip file from below given links.
Category 5, microservices, and modern architecture.
The monolith is dead. Modern applications are distributed across dozens of microservices, event buses, Kafka, and GraphQL endpoints. The old strategy of spin up everything and run E2E tests is too slow and too brittle for this world. In this section, we explore how architects test distributed systems in isolation using contracts, event polling, and observability hooks.
Scenario 23. Consumer-driven contract testing.
In a microservices architecture, Service A, frontend, calls Service B backend. If Service B changes a JSON field name, Service A breaks. Junior engineers try to catch this by spinning up both services in a dedicated environment and running heavy integration tests. This is slow and expensive. The architect's solution is consumer-driven contract testing, PACT. Before code problem, the integration test heavyweight. Disclaimer: always test code in a non-production environment. This test creates a hard dependency. You cannot test service A unless service B is live. If you have 50 services, managing a stable environment where they are all green simultaneously is an operational nightmare.
The solution: PACT contract testing.
We use PACT. The consumer service A defines a contract, a file stating exactly what it needs. For example, I need a field called username. This contract is generated during the test run against a mock. Later, the provider service B verifies this contract file against its real code. No two services ever talk to each other directly, yet we guarantee they are compatible. After code solution, defining the PACT. Disclaimer: always test code in a non-production environment. We strictly define the shape of the data we expect. This code generates a JSON PACT file. We upload this file to a PACT broker. The test runs against a lightweight mock server spun up by the PACT framework. It is instant, requires no network, and never flakes. If the test passes, we know our client code handles the contract correctly.
Follow-up 1. This tests the consumer. How do we ensure the provider actually follows this contract?
Answer: that is the second half of the process. In the provider's CI pipeline, we run a PACT verification task. It downloads the PACT file from the broker and replays the requests against the actual provider IPI. If the provider returns user_name instead of username, the build fails immediately.
Follow-up 2. Why not just use Swagger or Open API schemas for validation?
Answer: schemas, Swagger, are provider-driven. They say what the API can do. Contracts PACT are consumer-driven. They say what the API must do for a specific client. Swagger does not tell you if removing a field will break a specific mobile app version. PACT does.
Follow-up curveball. How do you handle authentication OAuth in PACT tests without hitting a real identity provider?
Answer: you mock it in the contract. You define that when a request comes with header authorization, bearer XYZ, the provider should accept it. On the provider verification side, you configure the test middleware to bypass signature validation for that specific mock token, ensuring you test the IPI logic, not the auth0/octa uptime.
Pro tip: the PACT broker.
To make this scale, use a PACT broker or PACT flow. It acts as a central hub. It creates a matrix that tells you, can I deploy consumer version 1.2 with provider version 3.5? You add a check in your CI/CD, can I deploy? If the matrix says no, the pipeline blocks the release automatically.
Scenario 24. Testing asynchronous events, Kafka.
Modern systems are event-driven. You click buy, the IPI returns 202 accepted, and a message is pushed to Kafka. Minutes later, a worker processes it and updates the order status. Junior engineers handle this by putting a massive thread .sleep, 60,000, hoping the event finishes. This makes tests incredibly slow and flaky. Before code problem, the hopeful sleep. Disclaimer: always test code in a non-production environment. This is purely arbitrary. If the queue is empty, the process finishes in 1 second and you waste 59 seconds. If the queue is backed up, it takes 61 seconds and your test fails. It is loose, unscientific, and unscalable.
The solution: awaitility polling.
The architect's approach is to poll for state change. We use awaitility to repeatedly check the side effect of the event, for example, the database status changing or a new record appearing. We do not sleep. We actively probe the system until the condition is met. After code solution, Smart state polling. Disclaimer: always test code in a non-production environment. We set a generous upper limit 2 minutes to handle load but a frequent check interval 2 seconds. This means if the system is fast, the test finishes in 2 seconds. If it is slow, the test adapts. No time is wasted. We focus on the outcome. We do not care about the Kafka topic or the consumer internals. We care that the data eventually reach the completed state in the database.
Follow-up 1. Why not just subscribe to the Kafka topic directly in the test and wait for the message?
Answer: you can, but it is complex. Kafka topics often have millions of messages. Filtering for your specific test message requires a unique correlation ID. Also, just because a message arrived on Kafka does not mean the database is updated yet. Polling the final destination, DB, is a more reliable end-to-end verification.
Follow-up 2. What if the event fails processing and goes to a dead letter QDLQ?
Answer: your awaitility block will time out and throw an exception. To debug this, your on-failure listener should check the DLQ topic for any messages related to your order ID and print the error reason to the test logs.
Follow-up curveball. How do you test idempotency here? What if the event is delivered twice?
Answer: you modify the test to fire the trigger twice explicitly. Then, use awaitility to confirm the status is completed, and check that the processed_count or audit_log in the database shows exactly one execution, proving the system handled the duplicate correctly.
Pro tip: injectable trace IDs.
When testing async flows, generate a unique trace ID in your test, for example, a UUID, and inject it into the IPI header. Ensure your system logs this ID across Kafka and microservices. If a test times out, you can search Splunk or Datadog for this one ID and see exactly where the message got stuck.
Scenario 25. GraphQL automation.
GraphQL changes the rules. Unlike REST, where you hit different URLs for different data, GraphQL has one endpoint. Junior engineers treat GraphQL requests like massive, messy strings inside a post body. If the schema changes, they have to manually find and replace text inside these strings across hundreds of tests. We need a typed, object-oriented approach. Before code problem, the string concatenation hell. Disclaimer: always test code in a non-production environment. This is unmaintainable. Escaping quotes / makes it unreadable. If you need to parameterize this, for example, getting a hero by ID, you end up with messy string concatenation plus ID plus, which is prone to syntax errors.
The solution: object-oriented query building.
The architect's approach is to treat the query as an object. We use a POJO, plain old Java object, or a dedicated GraphQL builder library. We serialize this object into JSON automatically. This provides type safety, compile time checking, and clean, reusable code. After code solution, typed payloads. Disclaimer: always test code in a non-production environment. We separate the structure query from the data variables. This allows us to reuse the same query string for thousands of tests, just changing the map of variables. It mimics how developers actually write GraphQL. We rely on the serialization library, Jackson or JSON, to handle formatting. This eliminates syntax errors caused by missing braces or escaped quotes.
Follow-up 1. How do you verify the schema itself has not broken? For example, a field type changed.
Answer: you do not do this in functional tests. You use a schema validation tool. You fetch the introspection query __ schema from the endpoint and compare it against a gold copy schema file stored in your repo. If they differ, the test fails before running any logic.
Follow-up 2. Can we use standard REST assured for GraphQL?
Answer: yes, as shown in the example. GraphQL is just HTTP post under the hood. However, for complex assertions, libraries like REST assured GraphQL or clients like Apollo for JS provide better helpers for navigating the specific data and errors JSON structure.
Follow-up curveball. GraphQL always returns HTTP 200, even if there is an error. How do you assert failure?
Answer: this is a classic trap. Status code 200 is meaningless in GraphQL. You must inspect the response body. You assert that the errors array is either empty for success or contains the specific error message code you are testing for negative tests.
Pro tip, fragment reuse.
GraphQL allows fragments reusable chunks of fields. In your framework, define common fragments, for example, user fields, order fields, as static strings. Concatenate these into your queries. This ensures that if you add a field to the user object, you update it in one fragment, and all 50 user-related tests update automatically.
Scenario 26, observability in tests, trace IDs.
When a test fails with 500 internal server error, the logs are usually useless. You just know that it failed, not why. In a microservices mesh, that request hopped through 5 different services. Junior engineers waste hours asking devs to check the logs. Architects inject trace IDs to make debugging instant. Before code problem, anonymous requests. Disclaimer, always test code in a non-production environment. This request looks exactly like thousands of other requests hitting the server at the same time. If it fails, the developer has to guess which log entry corresponds to your test run. It is a needle in a haystack.
The solution, trace ID injection.
The architect's approach is to generate a unique correlation ID, UUID, for every test. We inject this ID into the HTTP headers. Modern observability tools, Datadog, Splunk, Jaeger, automatically index this header. On failure, we print this ID to the report. The developer just copies the ID, pastes it into Splunk, and sees the entire request lifecycle. After code solution, header injection. Disclaimer, always test code in a non-production environment. We tag the request. Xcorrelation ID links all microservice logs together. Xtest name tells the developer exactly which test case generated this traffic, removing ambiguity. This is the payoff. When the test fails in Jenkins, the console log gives the developer the key to solve the puzzle instantly. No more can you reproduce this. Conversations.
Follow-up 1. Do we have to add try-catch blocks to every single test method?
Answer no, that would be messy. You implement this in a request filter, rest assured, or an interceptor, HTTP client. The filter automatically generates the ID, adds the header, and attaches it to the test NG or Allure report context automatically for every request.
Follow-up 2. What if the backend system uses a different header name, like traceparent?
Answer, this is part of your framework configuration. You should have a config.properties file defining header.trace.name. If the backend moves to the W3C standard, traceparent, you change the config in one place, and all tests update.
Follow-up curveball. Can we inject these headers into Selenium UI tests too?
Answer, yes. In Selenium 4, you can use the DevTools network domain, driver.getDevTools::create_session to intercept outgoing network requests from the browser and inject headers dynamically. Alternatively, you can use a browser extension or a proxy, like Browser Mob, to add headers to traffic leaving the browser.
Pro tip, link integration.
Take it a step further. In your reporting tool Extent or Allure, turn the trace ID into a hyperlink. https://splunk.company.com/search. Q equals trace ID. Now, when a manager or dev opens the test report, they are one click away from the server logs. That concludes microservices testing. We have moved from monolithic E2E tests to agile contract tests, async polling, and observable API calls. But functional correctness is not enough. Is the app secure? Is it accessible? This brings us to the final frontier, Category 6, specialized testing.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem solving, generally most asked, and system design. Required for your software testing, job interviews like automation test engineer jobs, QA analyst jobs, performance test engineer jobs, API tester jobs, Playwright automation test engineer jobs, DevOps test engineer jobs, automation test architect jobs, mobile application test engineer jobs, SDET, tester jobs, etc., etc. These questions and answers are carefully curated by industry experts. saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes real-world problem-solving interview questions and answers where almost 80% of the people are failing to answer. Scenario-based questions and answers. System design questions and answers where almost 90% of the people are failing to answer. With detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 6 PDFs in a single zip file from below given links.
Category 6, Specializations, Security, Accessibility, AI.
Functional correctness is just the baseline. A feature can work perfectly but still be illegal accessibility violations or dangerous security vulnerabilities. In this final section, we look at how the modern SDET expands their role into quality engineering, integrating specialized checks directly into the automation pipeline.
Scenario 27, Accessibility Automation, A11Y.
Accessibility WCAG compliance is often a manual audit done weeks after development. Junior engineers ignore it entirely. The architect's solution is automated accessibility injection. We integrate tools like AxeCore directly into our Selenium or Playwright tests. Every time a functional test runs, we automatically scan the page for contrast issues, missing labels, and broken area tags. Before code problem, the functional blinders. Disclaimer: always test code in a non-production environment. This test gives a false sense of security. The feature works, but if your company is sued for ADA non-compliance, this test provided zero protection.
The solution, AxeCore integration.
The architect's approach is to use the Axe Builder library. With 3 lines of code, we can inject the Axe auditing engine into the browser, scan the current DOM state against WCAG 2.1 AA standards, and fail the test immediately if violations are found. After code solution, automated audit. Disclaimer: always test code in a non-production environment. This analyzes the entire page structure instantly. It checks for color contrast, missing alt text, duplicate IDs, and bad area roles. We treat A11Y bugs as first-class citizens. If the page is not accessible, the build breaks, forcing the developer to fix the HTML semantic structure immediately.
Follow-up 1. Can Axe catch 100% of accessibility issues?
Answer: no. Automated tools can only catch about 30 to 50% of issues, syntactic errors. They cannot catch semantic issues, like whether the alt text actually describes the image meaningfully, or if the tab order makes logical sense. Manual testing is still required, but automation handles the low-hanging fruit.
Follow-up 2. We have a legacy app with 500 existing violations. Turning this on will break every build. What do we do?
Answer: you use a baseline strategy. You scan the app once and mark the 500 violations as known issues or ignored. The test is configured to fail only on new violations, the delta. This allows you to stop the bleeding while slowly fixing the technical debt.
Follow-up curveball. How do you test accessibility for dynamic states, like a modal opening or a drop-down menu expanding?
Answer: you must trigger the scan after the interaction. Automation shines here. You script, click modal parentheses leads to axe.analyze parentheses leads to close modal parentheses. Doing this manually for every state is tedious. Automation ensures every UI state is compliant.
Pro tip: component testing.
Ideally, move this check even earlier. Use Storybook or unit tests to run Axe against individual components, buttons, nav bars, before they are even assembled into a page. This shifts accessibility testing all the way to the left.
Scenario 28. Security injection, OWASP ZAP.
Security testing usually happens once a year, penetration testing. Junior engineers assume security is not their job. The architect's approach is security as code. We integrate a proxy scanner like OWASP ZAP into the automation suite. As our functional tests navigate the app, ZAP passively scans the traffic for vulnerabilities like XSS, CSRF, and missing security headers. Before code problem, the security blind spot. Disclaimer: always test code in a non-production environment. If a hacker entered script alert, hacked/script into this field, the application might execute it. This functional test would pass happily, completely missing a critical vulnerability.
The solution, proxy-based scanning.
The architect's approach routes the Selenium traffic through the OWASP ZAP proxy. The automation does what it always does, clicks and types, but ZAP watches in the background. After the test suite finishes, we query the ZAP API to see if it detected any alerts. After code solution, ZAP integration. Disclaimer: always test code in a non-production environment. We configure the browser to route all traffic through localhost 8080, where OWASP ZAP is running. ZAP effectively becomes a man in the middle for our test execution. After the tests finish, we ask ZAP, did you see anything bad? If it found high-severity issues, like missing X-frame options or SQL injection indicators, we fail the build.
Follow-up 1. What is the difference between passive and active scanning in this context?
Answer: passive scanning just looks at the traffic headers, cookies, without attacking. It is safe and fast. Active scanning actually attacks the app, injects malicious payloads. In CI/CD, we usually stick to passive scanning to avoid crashing the server or taking too long.
Follow-up 2. Will not this slow down the tests significantly?
Answer: passive scanning adds negligible overhead. However, active scanning is very slow. The strategy is to run passive scans on every commit (SCI) and trigger a full active scan only on a nightly or weekly schedule.
Follow-up curveball. ZAP works for HTTP/web. How do we test security for SOAP or gRPC API?
Answer: ZAP has plugins for SOAP. For gRPC or generic APIs, you might look at other tools like StackHawk or specialized fuzzers. The architectural pattern remains the same: proxy the traffic or replay the request with malicious payloads.
Pro tip: false positives.
Security scanners generate a lot of noise, false positives. You must implement a baseline or filter mechanism. Just like with accessibility, you need a config file that says ignore warning times on URLY so that the pipeline only breaks on new or critical issues.
Scenario 29. Chaos engineering in automation.
A test suite that only runs against a perfectly healthy environment is a fantasy. In the real world, networks lag, APIs return 500 errors, and databases time out. Junior engineers see these as flaky tests. The architect's approach is to induce chaos intentionally using tools like Toxaproxy or Chaos Mesh to verify that the application's resilience patterns, like circuit breakers and fallbacks, actually work. Before code problem, the happy path assumption. Disclaimer: always test code in a non-production environment. This test only validates the successful scenario. It gives zero confidence that the application can handle a partial outage gracefully. If the inventory service times out, the user sees a generic 500 error page.
The solution: injecting failure Toxaproxy.
The architect's approach is to programmatically break the system. We use Toxaproxy to create a toxic proxy between our application and its dependency. We can tell it to add latency, return garbage data, or cut the connection entirely. We then assert that our application handles this chaos gracefully. After code solution, controlled chaos. Disclaimer: always test code in a non-production environment. We are intentionally breaking the network. We are telling the proxy that connects to the inventory service to have an instant timeout. This simulates a complete service outage.
Follow-up 1. Does this require changes to the application code?
Answer: yes. The application must be configured to route its traffic through the Toxaproxy server instead of directly to the dependency. This is usually done with environment variables in the CI/CD pipeline, so it only affects the test environment.
Follow-up 2. Can we run these chaos tests in production?
Answer: yes, but very carefully. This is called a game day. You run controlled chaos experiments on a small percentage of production traffic during off-peak hours to validate that your alerting and auto-failover mechanisms are working as expected.
Follow-up curveball. The chaos test passed, the app handled the error, But our monitoring alerts did not fire in Datadog. Is that a pass or a fail?
Answer: that is a critical failure of observability. The test itself should assert that the alert was triggered. We should have a step that queries the Datadog, a PI, to ensure the PagerDuty alert was created. A silent failure is one of the most dangerous failure modes.
Pro tip: Kubernetes native chaos.
If your application runs on Kubernetes, use a tool like Chaos Mesh or Litmus Chaos. They can kill specific pods, hog CPU, or inject network latency at the Kubernetes level, which is a more realistic simulation of infrastructure failure than a simple proxy.
Scenario 30: Mobile versus web convergence.
An organization has a responsive web app and a native mobile app, iOS or Android. Junior teams create two separate automation suites, Selenium for web, Appium for mobile, duplicating test logic, locators, and maintenance effort. The architect's solution is a unified test core that shares the business logic and separates the platform-specific implementation.
The solution: the adapter pattern.
The architect's approach is to abstract the business flow. We create a generic login page interface and have two concrete implementations, web login page and mobile login page. A factory decides which implementation to use. The test script just calls login page.login parentheses and does not care if it is running against a browser or a native app. After code solution, abstracted logic, disclaimer, always test code in a non-production environment. We define the contract. This says what a login page must do, but not how. This is the core of separating business logic from implementation. The test is now clean and platform agnostic. This single test can be run against web, iOS, and Android without changing a single line of code, just by changing a configuration parameter.
Follow-up 1: How do you handle locators that are different between web and mobile?
Answer: you abstract them. The iLogin page might have a method getLogin button parentheses. The web login page returns by .css selector, #login, while the mobile login page returns mobile by .accessibility_id, login_button. The business logic just calls the abstract method.
Follow-up 2: What about BDD or Cucumber? Can we share feature files?
Answer: absolutely. This is where the pattern shines. You have a single login.feature file. You then have two sets of step definition files, web login steps.java, mobile login steps.java, that bind the generic Gherkin steps to the platform-specific page object implementations.
Follow-up curveball: The web app uses a hover menu, but mobile requires a long press to reveal it. How do you handle this in a shared test?
Answer: the business step is abstract when I open the user menu. The web steps implementation calls actions.move to element parentheses.perform parentheses. The mobile steps implementation calls touch action.long press parentheses.perform parentheses. The abstraction layer, the interface, hides these platform-specific details from the test itself.
Pro tip: Visual testing convergence.
You can even unify your visual testing. A tool like Applitools can take a screenshot from both your Selenium and Appium runs and compare them in a viewport mode. This allows you to automatically verify that your brand's look and feel is consistent across all platforms.
The end of the road.
That concludes our journey through 30 advanced automation scenarios. We have moved from basic scripting to designing frameworks that are scalable, reliable, and integrated into the DevOps lifecycle. You now have the architectural patterns to solve the real-world problems that separate junior testers from principal automation architects. You are no longer just a tester. You are a quality engineer. You are an architect.
Please check description or comment section of this video. I have given a lot of links for downloading 6 PDFs containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, and system design. Required for your software testing job interviews like automation test engineer jobs, QA analyst jobs, performance test engineer jobs, API tester jobs, Playwright automation test engineer jobs, DevOps test engineer jobs, automation test architect jobs, mobile application test engineer jobs, SDET, tester jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes real-world problem-solving interview questions and answers where almost 80% of the people are failing to answer. Scenario-based questions and answers. System design questions and answers where almost 90% of the people are failing to answer. With detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 6 PDFs in a single zip file from below given links. For more exciting tips, tricks and more importantly, for valuable insights of interviews, please share, like, and subscribe to my channel. It has a lot of valuable information about various insights of interviews. It has a wide range of real-world portfolio projects of various technologies for interviews, and it has wide range of most asked interview questions and answers of various technologies like data science, SAP, AWS, DevOps, and full-stack web development, and more. That will be useful during interviews. It has a wide range of most asked interview questions and answers and real-world portfolio projects of various technologies for freshers, for 2 to 3 years, experienced candidates, and for 5 or above years, experienced candidates to test their skills by knowing most asked interview questions and make themselves ready for interviews.